Now we have two random variables, and also we have joined PDF. We need to find the function of two random variables, z. Now I know the PDF. When we want to find the PDF, first we can find the CDF of that random variable, and then take the derivative of that random variable. Then we can get the PDF. So we can find the CDF first and then PDF. So let me find the CDF of z first. The CDF of z, from the basic definition, that's the probability of z that stands on certain point called z. Now since z is a maximum x and y, so I can also say this is the probability of maximum xy less than the certain point z, lowercase z. What does the maximum of xy less than z? For example, maxima 2, 4 is 4. Maximum 10, 0.1 is 10. So no matter this number or this number, I got always less than z. That means this is the probability of x will be less than z, and can put and y is also less than z. And that means x less than z and y less than z. They are also independent. Why? Because you can see that they can separate. This is the function of x and y. There are no correlated terms. So this is the probability of x less than z times probability of y less than z. This I can say this is the PDF of x, PDF of y. So now what does the probability x less than z means? That's a CDF of x. Similarly, this is a CDF of y. Then I want to find the PDF of z. You just take the derivative of z, of CDF z here. And we know the CDF of z actually is the CDF of x of z times CDF of y of z. And we know that actually e to the minus 1/2 x squared and e to the minus 1/2 y squared, they are the same type. That means the CDF of x is the same as CDF of y. Why? Because here I can have this times this. Then each x and y actually are Gaussian, mean 0 and variance 1. So the f of z, I just take the derivative of either CDF of x squared. That means the chain rules is to x, and then divided by z here, then it's the PDF of a z, a PDF of a x. Then which is, this is just a Gaussian. I can put this Gaussian form n times the PDF of x. Again, people may ask why you know the x and y individually, the PDF is Gaussian. So we just analyze this one. I can write it down like 2 pi times exponential 1/2 x squared times 1 divided by square root of 2 pi exponential to the minus 1/2 times y squared. And this one is Gaussian, mean 0, Gaussian, mean 0, and variance 1. This is also Gaussian, mean 0 and 1. So first they can separate, so the x and y are independent. And they are both Gaussian with mean 0 and 1, variance 1. So second, we want to find the minimum x and y PDF. So first we still find the CDF first of C of z is just the probability of the random variable z less than some certain point. Here we give it as a lowercase z, and since z equals the minimum xy less than z, now minimum xy less than z, I cannot do like the same thing as part A, like x is less than z or y less than z. Why? Because minimum 2, 5, you choose 2. Minimum 10, 1, you choose 1. You choose 2 and choose 1, but this number may probably greater than z, so it doesn't work. But we have a very lovely expression or concept like this. I can always have 1 minus probability of minimum xy greater than z. It's like probability A equals 1 minus probability A complement. So if the minimum is greater than z, that means the minimum greater than z, two numbers definitely always greater than z. So it means x is greater than z. Of course, y is greater than z. And because they are independent, so this times this is just 1 minus the CDF of x z times 1 minus CDF of y z. And you know that CDF of x equals CDF of y. So actually those terms are 2 times the CDF of x of z minus CDF of x over z squared. So I can find the PDF now. The PDF of z, I should take the derivative of CDF over z, which means 2 times the PDF of x of z minus 2 times the CDF of x times the PDF of x. And then I give you the answer here is this form: 1 minus the Gaussian function of